Okay, good afternoon, ladies and gentlemen, and welcome to your SETI Institute Colloquium series. Is that good? I'm Frank Marchis. I'm going to be the host for this colloquium today. Let me introduce our speaker, Jeremy Tregloan-Reed. He's a NASA postdoctoral fellow research fellow at NASA Ames, not too far away from us. His main research interest is basically the transiting exoplanet and the abiotic oxidation of the early Earth and terrestrial exoplanets. He completed his undergrad studies at Lancaster University in UK between 2006 and 2010. Between 2010 and 2014, he was a STFC-funded PhD research student at Keele University at Staffordshire in UK as well. He was awarding his PhD for the thesis entitled Starspot Properties and Photometric Parameters of Transiting Exoplanet and Their Host Stars. During his PhD, he has used various codes and did some work on modeling the transit of exoplanet around WASP-19 and WASP-50. So today is going to give a talk entitled Starspot and the Dynamic Evolution of Hotspot Jupiter Exoplanet Systems. And he will describe what we call the nuisance in the study of exoplanet transit, which are in fact the starspot, active region on distant stars. These starspot anomaly are found in transit, as I say, but they provide a lot of information on the star itself, such as the stellar rotation at a given latitude, but also information on the planetary system if the star is known to have a planet, such as the stellar obliquity of the system. So let's start welcoming first Jeremy, and you can start to talk. Okay, so this is good.
Okay. Thank you. Hello everyone, my name is Jeremy Tregloan-Reed and I'm an MPP Fellow at the NASA Ames Research Centre, and I thank you for joining me on this SETI seminar series where I'll be giving a talk on starspots and the dynamic evolution of hot Jupiter exoplanet systems. I'll begin with a brief overview of what I'm going to be talking about today, starting with the dynamical evolution of hot Jupiters, which they will then go on to talking about the stellar obliquity and the Rossiter-McLaughlin Effect, which is a Doppler spectral measurement of the sky projected spin orbit alignment of the system. I'll then be moving on to starspot anomalies and exoplanet light curves and how they manifest and why they manifest. I'll then be talking about the current methods of modelling the starspot anomalies and how starspots, the stellar rotation and the stellar obliquity can be all linked together. I'll then be talking then about the transit and starspot modelling using the code I created during my PhD called PRISM. I'll be talking about how it models for stellar disk and transit and then how it models for starspots. After that, I'll then be moving on to talking about GEMC, or Genetic Evolutionary Markov Chain, which is an optimization algorithm I constructed alongside PRISM. I'll be talking about the conceptual workings of GEMC, the performance of GEMC compared to the genetic algorithm Pikaia, and the forward simulation of synthetic data. I'll then be talking about analysing of live data of transit light curves of WASP-19, WASP-6 and HATS-2. And I'll then be finishing off some brief conclusions about which is better, the RM effect or starspot method. Is there a statistical trend we can see in the results? And then I'll be moving on to tidal timescales and stellar effective temperatures and how they all link together with stellar obliquity. Right. First of all, the dynamic evolution of hot Jupiters. Basically, what we're talking about is a Jupiter planet must form beyond the snow line of the system, but how does it come so close to its host star? So there's different migration mechanisms, and one of which is called disk migration, where the planet's orbit evolves with the disk, the protoplanetary disk that it forms in. There are two main types of disk migration, type 1 and type 2 disk migration. Now, the main key difference between the two is the planet large enough to clear its orbit of debris? If the answer is no, then during its orbit, the planet will interact with the Limbad resonance sites and will experience differential torque, which will push the planet in a decaying orbit towards the host star. Now, if this decay rate is faster than the lifetime of the disk, then the planet will end up colliding with the star and being eaten up before the disk dissipates. If though the decay rate is slower than the lifetime of the disk, then the disk would dissipate, leaving the planet in a close orbit close to its star. Now, if the planetary orbit at the beginning is eccentric, i.e. it's an elliptical orbit, it will also interact with the co-rotation sites, which have an effect of dampening the eccentricity, leaving the orbit circularized. Now with type 2 disk migration, the planet is large enough to clear its orbit of debris, and as such, it then becomes tidally locked with the disk. So it will move with the disk to either towards the star or away from the star, depending on its position and the angular momentum. In either case, with both type 1 and type 2 disk migration, the orbital inclination and eccentricity are damped, leaving the planet aligned with the protoplanetary disk. So if the disk is aligned with the rotation period of the star, the planet will be left aligned with the star. But if the disk is misaligned, then it will leave a misaligned planet, i.e. the orbital inclination is slightly shifted from the rotational axis of the star. Now, there are also other mechanisms, such as gravitational scattering, gravitational ejections, and Kozai cycles, and these tend to happen once the disk is dissipated. And what these tend to do is kick the planet into either towards close to the star or give it a very large eccentric orbit. And for example, with gravitational scattering, two planets come very close together and kicks one planet towards the star and clicks another planet out the star. But that explains how the planets get an eccentric orbit and misaligned orbit, but how does it explain they get so close to the host star? And then you have tidal dissipation, where if you think of a comet, it starts very far out from the star system, and when it comes towards the sun, it gets very close to the sun. So for when the planet does it to its own star, it's only a few stellar radii from the star, and you get tidal dissipation from the star, and it ends up circularizing the orbit and causing it to circle a very close orbit to the host star. But in these cases, we always have a misaligned system. So effectively, if we can measure the spin-orbit alignment of the system, we can determine what's the dominant process involved in, which is the dominant migration mechanism involved in the formation of the system. And that's what I just spoke about. Okay, the stellar obliquity, or the measurement of the angle between the stellar rotation axis and the orbital plane. It is a fundamental geometric property. When you combine it with the semi-major axis, the orbital eccentricity, and the orbital inclination, you get a full geometric model of the planetary system. Generally, though, it's not possible to measure psi, but it is possible to measure the sky projected spin orbit alignment. So basically, if you're looking at your star, you've got your axis of the star pointing upwards. The orbital axis of the planet could be tilted like this. So the planet's orbiting almost from pole to pole. And once you know what lambda is, you can then start to derive statistical constraints on psi. So what is the connection between psi and lambda? Well, using this equation here, if we look at a transiting system, the orbital inclination has to be close to 90 degrees, because if it isn't, the planet won't transit the star from our viewpoint. Hence, this second term here, because of the cos of the orbital inclination, becomes 0, so we can ignore this second term, and this sine I naught becomes 1. So effectively, the cosine of psi equals the sine of the stellar inclination angle multiplied by the cosine of the sky projected spin orbit alignment. Now, because we don't know what the stellar inclination angle is, which basically 90 degrees is pointing straight up from us, 0 degrees is pointing towards us, and the star's rotating around in a circle from our viewpoint, sine I effectively ranges between -1 and 1. So cos psi will always be less than cos lambda, which therefore, when we take into account our cosines, psi is always equal to or larger than lambda. Now this has an interesting effect. If we measure lambda to be 90 degrees, then psi has to also be 90 degrees, and we have a misaligned system. But if we measure lambda to be only a couple of degrees, then psi could be anywhere from a couple of degrees to 90 degrees, and even though we measure an aligned system, we could still have a misaligned system. Right, the Rossiter-McLaughlin effect. Basically, it's Doppler spectroscopy. You have a star, and it's rotating towards you. The hemisphere that's rotating towards you, the light will be blue shifted, while the hemisphere that's rotating away from us will be red shifted. Now, the spectral light, it broadens the spectral lines, but when you integrate the total starlight, it has no effect on the total integrated starlight. But during a planetary transit, the planet blocks out a portion of the light of a hemisphere that's rotating. So this effectively destabilizes the balance between the integrated starlight, and so we end up getting a net blue shift when the planet is crossing the hemisphere rotating away from us, and you get a net red shift when the planet is crossing the hemisphere of the side that's rotating towards us. And this effect is known as the Rossiter-McLaughlin effect. Okay, this is a little schematic showing the dependence of the RM anomaly shaping RV data compared to on lander. If you look at the left, image, when we have lander equals 0 degrees, the planet spends equal amount of time in both hemispheres. As a consequence, the RM anomaly is symmetrical at both sides. When we increase lander, we end up destabilizing the balance, and the planet spends more time in one hemisphere more than the other side. Hence, we start breaking the symmetry in the RV anomaly. And in the case of on the right-hand side, where we have lander equals 60 degrees, the planet only transits one hemisphere. As a consequence, we only see an effect, only a blue shifted effect. So by measuring the shape of the RM anomaly, we can determine what lander is. Okay, we have some examples here from WASP 18 and WASP 19 of the RM anomaly. As you can see, in both cases, in the middle panel, the RM anomaly is roughly symmetrical. Hence, we can determine that lander is in fact close to 0. In WASP 18, it's 13 degrees. In WASP 19, it's 15 degrees. But one of the things I wanted to show was, if you look at the uncertainty in WASP 18, we've got plus or minus 7 degrees, while the uncertainty in WASP 19 is plus or minus 11 degrees. And that can be seen by looking at the middle panel. For WASP 18, the noise in the data is very low. The model actually fits the data very well. Well, compared to WASP 19, there's a lot of noise in the data. And so the model doesn't fit very well, hence you get a large uncertainty in the measurement. And the reason being is because WASP 19 is an active star with star spots. And I'll be going on to that in a minute. Right, starspot anomalies and exoplanet light curves. In transit photometry, we're effectively measuring the change of brightness of a star in respect to time. So as a planet transits across the star, it blocks out a portion of light, and we get a dip in the total light from the star, and we end up getting a transit shape. Now, star spots have a different effective temperature compared to the surrounding temperature, and as such, they emit a different amount of flux. Now, because the planet is mapping out the change of brightness as it transits across the star, by moving from an unspotted section to a spotted section, we'll get a blip in the transit light curve as the change in flux. Here is an example of HD 209458, which contains a star spot anomaly. And as you can see, we begin out of transit data. The transit begins, the planet's now eclipsing the star, and at this point here, it then crosses from the photosphere to a star spot. And as a consequence, because the star spot is dimmer than the surrounding photosphere, the planet now blocking out less light than it was before it started transiting it. Hence, we get an increase in brightness just for the star spot. Now, there are different methods for modelling this. The standard approach, or the most general approach, is to model the star spot and transit separately. So basically, they look at the data points affected by the star spot, they either remove them or assign them a weight of 0, and they then model the transit, and they then look at the residuals, where they see the data points affected by the star spot, and use a Gaussian to model that. Now, there is a slight problem with that, as it has been shown that star spots affect the entire shape of the transit, particularly the transit depth. During the data reduction process, the outer transit is always scaled to unity. But that is not the case, because if you've got stars rotating on and off the disk of the star, the brightness of the star is oscillating outside of the transit. Hence, it's not actually 1 outside the transit, it's less than 1. So by having a star spot there, you're effectively, and normalising it to 1 outside the transit, you're affecting the transit depth, which then in turn affects the transit length and also the limb darkening coefficients. There are other models out there. There's the model by Silver that produced a model that allows the physical properties of a star spot inside the transit to be found. The problem with the model, though, is it only has the ability to fit the star spot parameters. So you must know what the physical parameters of the planetary system are before then. The radii, the inclination, the limb darkening coefficients, the orbital eccentricity, and you put them in as they are, and then it then fits for the star spot, which is great if you already know what the system details are, but if you don't, it can be a bit of a problem. There's also another code out there called Spot Oscillation and Planet, or SOAP, and there's the new improved version of SOAP-T. The strength of it is it actually models the transit and star spots simultaneously. The problem, though, is it's a web-based application, there's no source code available, and it only fits RV data. So you can't fit your photometric data from your transits, And the reason they've done it that way, as they explained, is if they use the transit data and also the RV data, they have 18 parameters to fit. And the problem is, using conventional MCMC algorithms, the chains tend to get trapped in local minima and have poor convergence. So, back to this light curve of HD 209458. The reason I'm showing this again is because this quite nicely explains how, using a starspot anomaly in a transit light curve, we can precisely determine the position of the starspot on the stellar disk. The planet has an inclination, or an orbital inclination, and it then cuts across the star an impact parameter. So it's mapping out a line of latitude across the star. So from that, we know the latitudinal position of the starspot. As I said before, the planet also transits across the star, so it's actually mapping out 180 degrees across the longitude of the star. So at the 0 point, we actually got the planet directly at the centre of the star, and so by measuring the time that the starspot anomaly is, we can actually determine the actual longitudinal position of the star. So by using this method, we can actually pinpoint the position of the starspot. So why is that good? Well, let's say we've got 2 transits. Each one's got a starspot anomaly. Between the time between the 2 transits, the star's rotated, so the starspot has now moved. We see this in light curves, where we have a starspot at the left-hand side of the transit and then the same starspot anomaly on the right-hand side of the transit a day later. So we've now got the position and time of the starspot at 2 different points of space and time. From that, we can then calculate the rotational period of the star, and also, using geometry, we can then calculate the spin orbit land of the sky projected spin orbit alignment of the system. So now go on to my code PRISM, which I developed during my PhD. It models the transit using 8 transit parameters, the ratio of the radii, which is effectively the transit depth, the sum of the fractional radii, and when I say the fractional radii, it's the absolute radii scaled by the semi-major axis. So we say the semi-major axis is 1 because we don't have any RV data, and then we scale the system up based on what we determine for the radius of the star using stellar evolution models. We have linear and quadratic limb darkening coefficient. I stuck to the quadratic limb darkening law. It's because quite a few researchers out there use the four parameter law. You only really need that when you're using space-based data, when your accuracy is a lot more equivalent. But when you're just using ground-based data, the quadratic law is quite sufficient. You have the orbital inclination, a reference transit midpoint, and in some cases the orbital eccentricity and the argument of periodization. Now the last 2 aren't actually fitted. You can't determine the orbital eccentricity and the argument of periodization from a transit light curve on its own. You could if you have an occultation, but with just a transit, we can't. But there are some planets out there that we have RV measurements, and we know what the orbital eccentricity and argument of periodization are, and we know that they have an effect on other parameters, such as the orbital inclination and R star, the radius of the star. So we use Gaussian priors in the code, so that way then we can statistically sample all the solutions in the Gaussian distribution. Now, for the star spots, there are 4 parameters for each spot. You've got the longitudinal position, the co-latitudinal position, and when I say the co-latitudinal position, we say 90 degrees is the equator and 0 degrees is the North Pole. We have the angular size of the spot. Now that's normally in degrees, where if you draw a straight line from the centre of the star to the centre of the spot, and you draw another straight line from the centre of the star to the edge of the spot, it's the angle between the 2 lines. And you have the contrast, where a contrast of 1 is equal to the surrounding photosphere contrast, and a contrast of 5 means it's half as bright. Sorry, 0.5 is half as bright. So if we wanted to model, say, 2 star spots in our transit light curve, we effectively got 16 parameters, and things can get a bit messy. PRISM is effectively a pixelization method. What it does, it creates the stellar disk on a set of Cartesian coordinates. It then creates a circular star spot using force cycling to create an elliptical shape on a 3-dimensional curve from a 2-dimensional perspective. And once it's done this, it then calculates the position of the planet for each data point, and then sums up the total flux value for the whole grid, and does this for every point inside the transit. Oh. Okay. Basically, what this figure was supposed to show was what we have is there's 9 outputs of a star spot rotating around the star, and it just shows just how PRISM is able to do an elliptical shape of the circular spot as it rotates around the curved surface of the star. Right, I'll now go on to my optimization algorithm GEMC. When we first attempted to fit PRISM to synthetic data, we used conventional MCMC algorithms, and it resulted in poor convergence, mainly because as a chain found a local solution, but no matter which direction it went in, it kept coming up with a worse solution, and so they kept getting stuck. So I then decided to go down the route of genetic algorithms, which are great global optimizers, but the problem with a genetic algorithm is you can't perform Bayesian statistical analysis. So we aren't able to determine the uncertainties in our parameters. So we've got MCMC, which can perform Bayesian statistical analysis and get our uncertainties, or we've got a genetic algorithm, which can find the best optimal solution, but is poor at determining the uncertainties. So after reading a paper on DEMC that was put forward by Turbrack, how DEMC works, it merges a genetic algorithm with MCMC. And basically you have thousands of chains operating simultaneously in each generation. But when it perturbs a particular chain, it randomly selects two chains, looks at the parameters, takes the difference, and then applies the perturbation to the chain it's perturbating. Now, when I looked at it originally, I thought that sounds great when you want to work out your uncertainties, but it doesn't seem very precise at minimizing to find the global solution. So I then altered it slightly and named it GEMC. Basically, what happens is GEMC, it has thousands of chains. It determines which of the chain in that generation is the best fitting chain at that particular generation. And then when it perturbs a chain, it looks at the difference between the chain that's been perturbed and the best fitting chain, calculates the difference in the parameter values, and then multiplies them with a random number between 0 and 2, and applies that to the chain. It then perturbs the chain. If it results in a better fit, it's accepted, and if it results in a worse fit, then it's only accepted based on the Gaussian probability distribution, just the same as MCMC. Right. Now, so basically we have here two equations for x1 and y1. This is just for two parameters. So obviously you had 10 parameters, there'll be x1, y1, z1, so on and so forth. And basically what we're showing is step 1 is equal to the previous step plus gamma times the difference in the parameter between the parameter and the best fitting parameter. And gamma, as I said, can range from, is a random number between 0 and 2, where if gamma is 0, the parameter doesn't change. If gamma is 1, the parameter will change to the best fitting parameter, and if it's 2, it will overshoot the parameter. The better way to explain it is looking at this figure here. Here we have a two-dimensional space with two chains. It's been determined that the chain here at the center is the best fitting chain. So we calculate the difference between the two parameters, delta x and delta y, and then we multiply it with a random number between 0 and 2. Effectively, what we have here is that the chain x0, y0 can be perturbed to any position within the blue box. And effectively, what that does is allows the chain to perturb in a vector towards the best fitting chain. Now, if you think about our 14-dimensional space with thousands of chains, in simulations and tests, it actually finds the optimum solution very quickly. But GEMC works in two stages. First of all is the burn-in stage, where it uses the method I've described here. But then once it's found the optimal solution, it then splits off and does DEMC to determine the parameter uncertainties. Right, the performance of GEMC. Basically, what we have here on the left-hand side is a plot of a function that was used to test the genetic algorithm of Picaya by Chabanu in '95. Basically, the function is the thing here on the right-hand side, and effectively what we've got is a surface with lots of local solutions, with the optimal solution at the dead center when x is 0.5 and y is 0.5. And what he showed was for an MCMC algorithm, it finds one of the local peaks, it goes to the top, but then it can't move any further because every time it moves somewhere, the bestness of fitness reduces. Hence, it keeps rejecting it and rejecting it and rejecting it, and the chain basically gets stuck there for thousands and thousands of iterations. So he derived this function, and when you use n, which is this bit here, say n equals 9, you basically generate 80 local solutions and one global solution. If you used n equals 12, you'll have 143 local solutions with one global solution. And so what we decided was to test GEMC on the same sort of function and compare the results to Picaya. Here on the left-hand side, we have the plot of the function evolution with generations. What they found with Pikaia is by the 20th generation of a population of 100 members, that's 2,000 function iterations, the genetic algorithm had actually found the global peak. They hadn't found the global point, but they found the global peak. With GEMC though, what we found was that they actually found the global solution in 5 generations. And that's with a population of only 40 chains. So that's only 200 function iterations, which is a tenth of the time. Here we have some outputs from one of the tests with the chains. We have here here we basically have a contour plot of the function with all the peaks, with the central peak being the optimal solution. This plot here is the initial random population where basically the parameters are randomized. As you can see, the 40 chains are all randomly around the parameter space. By the 10th generation, we've noticed that quite a few of the chains have already converged on the optimal solution. If you look at the value here at the top, 0.99999, the optimal solution is at 1. So they're very close to the optimal solution. By the 20th generation, they've actually found the optimal solution at 1.000. And by the 40th generation, all 40 chains have converged on the optimal solution. So, how does this work with synthetic data? Well, basically, we used PRISM with a fixed set of parameter values, which are shown here in this table, and created a light curve. We then added random noise to distribute it, and we assigned error bars to the data points so that the original model had a reduced chi-squared value of 1. We then used PRISM and GEMC to see if we could then find and recover the original parameter values. And what we found is, in all cases, it was able to find them within the 1 sigma uncertainties, which shows us that it actually can find the best fitting solution. But a case in point which we didn't expect, which is also a testament to the power of GEMC, is the original noise-free model had a reduced chi-squared of 1. The recovered solution had a reduced chi-squared of 0.94, which meant the recovered solution fitted the synthetic data better than the original model. Now, we thought, how is that possible? But then when you think about it, we added noise. So the parameter space is no longer smooth, it's jagged. So what GEMC's done is actually found there's a bit of noise and found the phantom solution close to the original model. So what we now do is GEMC not only outputs the best fitting parameter values, it also outputs us the mean of the top 5% of solutions. Okay, WASP-19. We have 3 transits of WASP-19, 2 consecutive transits, and then a few days later another transit. Now the orbital period of WASP-19 is approximately 19 hours, so it takes just 19 hours to orbit its host star. So the 2 starspot anomalies are separated by about 19 hours. And we can see on the first one we've got a starspot anomaly on the left-hand side of the midpoint, and on the right, and the next 19 hours later it's shifted to the right-hand side of the transit midpoint. So we've got these schematics here from PRISM, and we can see how the starspot has shifted across. Now, obviously the spot does seem a bit too large, but we're only actually measuring what's actually inside the transit cord. Yeah, we're only actually measuring what's inside the transit cord. So what we believe is really happening is we're not actually occulting a large spot, we're actually occulting a band of smaller spots or an active region. But from measuring the time frame it's taken for the spot to move from here to here and the distance upon it, we're actually able to calculate the rotational period of WASP-19 to be about 11.76 days, which is an excellent agreement to rotational modulation measurements of around about the same time period. We're also able to measure lambda, which is the sky projected alignment, and we basically draw a straight line between the centre of the 2 spots, and the vector of lambda is always at 90 degrees. So if the line is perfectly horizontal, lambda is 0 degrees. But if the line is slightly shifted, lambda is slightly shifted, and as a consequence, we can actually measure lambda. And in this case, we measure lambda to be 1 plus or minus 1.2 degrees. So we come to the conclusion that WASP-19 is in a very aligned system, but we still don't know what psi is. So one of my collaborators then used the Grand instrument on the Max Planck Institute ESO 2.2 meter telescope in LaSille, and with GROND they're able to simultaneously look at an object in 4 optical passbands and 3 infrared passbands. And this is the combination of the optical light curves in the G, R, I and Z filter. And as you can see, they've even detected another star spot in WASP-19. Now, as the star spot is always at the same temperature, but at the same time it's being looked in different bands. So the peak of the wave function for the star spot is always at a slightly lower, more redder wavelength than the surrounding star. So the star spot anomaly will always appear larger in a bluer band compared to a redder band. And as you can see, as we move from the green to red to I to Z bands, the star spot anomaly size is getting smaller and smaller and smaller. And once we move into the infrared, it virtually disappears, which is what we expect. Now, we can actually determine the temperature of the star spot using an equation from Silver, which is effectively the ratio of the effective temperature of the photosphere and the effective temperature of the star spot with the wavelength that you're looking at the star spot. Now, while you can do this with just a single wavelength, it is better to use multiple wavelengths like Luigi used here. And basically, you can calculate what the temperature of the star spot is in the 4 different bands and see if there's a correlation. And in this case, all of the temperatures agreed with each other, and they measured the star spot to be about 4,770 Kelvin, compared to the photosphere, which is around about 5,460 Kelvin. And so they then turned around and said, well, is this realistic? So they compared the temperature of the star spot to the temperature of the photosphere and compared that to other stars where star spot temperatures have been measured. And they found that WASP-19 quite nicely fits here in the plot with the other stars. So they came to the conclusion that it is a correct temperature. Right, on to WASP-6. We've got a similar situation here. We've got 4 light curves, 2 of which contain a star spot anomaly. The difference, though, and the problem with WASP-6, is the light curves are separated by 27 days. So we cannot categorically say that it's the same star spot, unlike WASP-19, where they're separated by 19 hours, so you can argue that it is. So we decided to model each of the 2 light curves completely separately and determine to see if the star spot properties are the same. And the photometric parameters of the star spots from the 2 nights actually agree with each other in contrast and size within the 1 sigma uncertainties. But that doesn't necessarily mean it's the same star spot. So we then turned around and said, well, if it is the same star spot, what would be the rotation period of the star and what would be the spin-orbit alignment? If it is the same star spot, we measure the alignment to be 7.2 plus or minus 3.7 degrees. And we also measured the alignment, the rotation period to be about 23.8 days. Now, I say 23.8 days, this is the one that we homed in on. Basically, in the 27 days between the anomalies, how many times did the star rotate? It could have rotated once and a little bit, or it could have rotated twice and a little bit. If it rotated once, its rotation period would be around about 23.8 days. If it rotated twice, plus 47 degrees, its rotation period is about 12.63 days. Now we can use that and the stellar radius to calculate the latitudinal surface velocity to be either 1.78 kilometers for 23.8 days, or 3.36 kilometers per second for 12.63 days. Now, there have been V-sin-I measurements of WASP-6 from Gilead and Doyle, and they determined V-sin-I is 1.4 plus or minus 1 kilometer per second, or V-sin-I equals 2.4 plus or minus 0.5 kilometers per second. Now, both these values for V agree with the V-sin-Is, and the main reason for that is we don't know what I is. Hence, any value of V that is found to be greater than V-sin-I can be considered to agree. But what we can say is, we know that there's obviously differential rotation taking place on the star. But because the star spot's positions are roughly only 10 degrees from the equator, we can argue that any differential rotation would be small. So any large divergence of V from V sin I would have to indicate that sin I is small, and therefore I is much less than 90 degrees. So effectively, if the stellar inclination angle is small, then psi, the true spin orbit alignment, has to be far from lambda. So we have 2 different solutions. We either have a fast rotating star that's with a misaligned planetary system, or we have a slower rotating star with an aligned system. Now, I'm going to talk a bit about statistical trends, but that's I'm more going to go into it later. But because WASP-6 is a cool host star, it's got a photosphere of less than 6,250 Kelvin, the statistical trend tells us that it's most likely an aligned system. So we predict that it's got a rotation period of 23.8 plus or minus 1.5 days, if the starspot anomalies are caused by the same starspot. Now, just recently there was a paper by Nikoloff on WASP-6 where they actually used the Hubble Space Telescope on WASP-6, and they also got some ground-based data, and they actually measured the rotational modulation of WASP-6 to be 23.6 plus or minus half a day, which is in excellent agreement to our to our rotation period if the star's only rotated once. Now, if that is the case, then we can argue that psi, which is the true spin-orbit alignment, has to be close to lambda, because the only way that we can have, I'll just go back. The only way that I has, if basically V is 1.78 and we're go back 2 slides there. If V is actually 1.78 and our V sin i's are 2.4 or 1.4 within the uncertainties, therefore the stellar inclination angle has to be close to 90 degrees for that to happen. So we predict that psi is 7 degrees. So basically we can use circumstantial evidence to form a statistical constraint on the true stellar obliquity compared from the sky projected obliquity. Now, there is another way to directly measure psi from star spots in transit light curves. I'm using this plot here of WASP-19 for 2 consecutive transits. When we determined lambda, we effectively drew a straight line between the 2 spots and calculated the angle of the line from the y-axis. Now, let's say it was possible to get a 3rd transit in between these 2 transits and they had the star spot. If that then allowed the star spot to also fall on the same line, it means that the stellar rotation axis has to be lying on the plane of the page. Hence, psi has to be equal to lambda. But if we had the 3rd transit and it had the star spot below or up, now obviously you can get latitudinal drift, but over a course of a few hours, it won't be that large. And it would be a bit weird to see a spot drop down then come back up again. So the only way that could happen is, because the star spot rotates along a line of latitude, is for the line of latitude to be curved. And the only way you can have a curved line of latitude is if the stellar rotation axis is pointed either towards or away from us. So if you're able to get 3 transits of a light curve and actually measure the curvature of the line of latitude, you can actually precisely determine what psi and the true obliquity angle is. Okay. HATS 2, or the Hungarian Automatic Telescope South 2. This was a paper by Molly Fisher et al., where they basically used GRON to determine the properties of HATS 2, and in both cases they determined a star spot in both cases. Now, in their analysis, they used all 4 bands for the first transit, but they only used the R, I and Z bands for the second transit. The reason being is because of their second anomaly here. Now, they believe it was due to a hotspot or a phage, which is basically a chromatic magnetic artifact in the chromosphere that is related to star spots. So as a consequence, they didn't actually model that particular light curve. But it was also shown by Silvia Valio that you can get more than 1 star spot anomaly in a transit light curve. Now, originally, PRISM was created so it can model more than 1 star spot at a time. But GEMC was coded to only model a 1 single star spot or no star spots due to the static coding of the input file. So since then, that's been changed to a more dynamic input file. So basically, you can put in your list of parameters, and GEMC can determine how many star spots you want to model. And as we can see here, for modelling the HATS 2 light curve that they didn't model due to the hotspot anomaly, we actually model it, and we actually can show that there is actually some sort of hotspot at this point just before the star spot. Whether that's a phage or not is still speculation, which has been going through the research group. Right, on to my conclusions. What's better, the RM effect or star spots in transit light curves? Well, from my opinion, they're both equal. The RM effect can be used to ascertain a value of lambda, so can the star spot method, and potentially can measure the true spin orbit alignment. The RM effect, though, can suffer from excess RV jitter, i.e. star spots. Therefore, the RM effect is best used on a magnetically quiet star or a system where the planet does not cross an active latitude. The opposite is true for the star spot method in light curves. We want the planet to cross a star spot. There is, I mean, for example, I went to collect data on WASP-50, and we decided to pick WASP-50 because the HK line showed magnetic activity and it looked like a good candidate. But out of 2 consecutive light curves, we saw no starspot anomaly, and in all other published data, there's no starspot anomaly. So we can't use the starspot anomaly to determine the spin-orbit alignment. But when we are able to use the the starspot anomaly to determine lambda, we tend to get it with a far higher position. As you remember when I was talking about earlier in the thing, using the RM effect for WASP-19, they had plus or minus 11 degrees uncertainty. While with the Starspot method, we got plus or minus 1.2 degrees of uncertainty. So we can get an order of magnitude better precision. Now this indicates that the Starspot method to measure lambda is superior to the RM effect. But the Starspot, as I mentioned, the Starspot method does not always work in obtaining a transit. So between the 2 methods actually complement each other. You would, ideally, if you could, use the Starspot method in a transit light curve. But then if that fails, you can always then perform your radial velocity measurements and determine it using the RM effect. Right, is there a statistical trend in what we can measure with the terms of the stellar effective temperature and lambda? Now this is a plot of about 80 odd planets where we have both the effective temperature of the star and the spin orbit alignment, and what we find is 75% of cool stars, and when I say a cool star we're talking about a temperature less than 6,250 degrees, tend to be in aligned systems. Well, for the hot stars, 56% tend to be misaligned. So it's more of a 50-50 that a hot star will have an aligned or misaligned system, while if it's a cool star, it will more generally be an aligned system. And this is a trend that was pointed out by Joshua Wynne, that cool stars with hot Jupiters will have low obliquities. So, can we really explain this? Well, I'm a bit cautious with respect. We only got about 80 odd data points, and so we draw the problem I had during small number statistics. In a few more years or decades where we've got results for thousands and thousands of stars, we might see a completely different trend. But the idea is that hot stars have thinner convective zones, and as a consequence, it takes longer for the photospheres to align with the planetary orbit. Because of this, when we examine the lambda value of hotter stars, because it takes longer for it to take place, more of the hot stars will have misaligned systems. Also, on average, cool stars live for longer than hotter stars, because we're talking about main sequence stars. As a consequence, when we look at a hot star or look at a cold star, the cold star statistically would be older than the hotter star. As a consequence, the alignment process has been going on for lots longer compared to the hotter star where the alignment process has been taken on shorter. Okay, thank you.
The floor is open for questions. We have one here already.
Hi. 2 questions, one very, very quick. The first one is, what's the longevity of an average star spot?
Ooh, now that's interesting. There's 2 different, well, it all depends. You've got I can't pronounce the guy's name. Basically, they're using models on the sunspot, where basically the lifetime of the spot is equivalent to the size and this constant, and they measure the constant for the sun. And so for a star spot with a size of 1 degree has a lifetime of about 30 days. But there's been other research recently that states that this constant is probably only applicable to the sun. And when they compare it to other stars, this lifetime that we thought, oh, this star spot can last for 2-3 months, actually it turns out to only last for a couple of about 10-15 days. But for WASP-6, using whichever model we use for Starspot to last 30 days, it has to be anywhere between, has to be greater than at least 8 degrees. And in the case of WASP-6, we determine it to be about 12-13 degrees.
Thank you. So my follow-up is, it occurs to me that one way to sort of verify the usefulness of your model, if you had data with multi-planet systems and 2 planets transiting the same star spot, are you planning to expand your use of the algorithm for that and compare it to observational data? Yes.
There are quite a lot of possibilities for PRISM and GEMC. Especially with GEMC being able to fit multiple parameters. I have thought about actually doing multiplanetary systems, and also about thinking about being able to allow it so it can actually fit multiple transit light curves, say for Kepler, where you've got continuous light curves, because with Kepler it'll be great. The problem is it's currently written in IDL, which is the interactive data language, And so before I start going down that route, I need to convert it to, say, Fortran, which is a bit faster.
Fortran?
Yeah. It's about 5 times faster when it comes to number crunching than IDL, or at least Python.
I didn't know anyone was running Fortran in the 21st century.
My PhD supervisor does.
Wow.
It's been updated a bit.
Yeah.
Has it since
Yeah.
I don't think you have to like put everything in column 7 anymore.
But yes, it is certainly one of the things I'm considering. Another thing I'm considering is, as I said, we've got 4 parameters for the Starspot. I'm thinking of adding a 5th parameter, eccentricity. That allows the Starspot to become elliptical. So that way we can have a band of spots. But there's quite a few people I've been talking to. Some say it's a great idea, others turn around adding a lot more degeneracy to the system. So
that brings me to one of the questions I had while looking at your last slides. Could you tell us a bit the context about what kind of new data you're expecting to get in the future, like in the next year, but also the next 10 years? Like what kind of space mission will be significantly interesting for you?
ooh. Well, the new JWST for my current research for detecting oxygen in exoplanet atmospheres or ozone. So for JWST, what was the other mission? I think it's in Europe, Gaia, which is the basically, if I got the name correct, it's basically where they got the cameras in all 360 degrees, so they can actually do, they can measure surface brightness of various stars from the whole sky perspective instead of just a very small field like Kepler does.
Any questions on this side?
My question is about one of your early charts where there were, I think, 3 different mechanisms that could bring a hot Jupiter close to the star.
Yes.
And I don't think you discussed one of them that there was a name assigned to it, K something or other.
Oh, Kozai cycles.
Kozai cycles, yeah.
Yes.
What's that?
I'll be absolutely honest with you, I only briefly touched it in my PhD thesis and I didn't really go into it much details. I just used it and cited it. I'll be honest.
Okay,
Okay.
I'll Google it.
Thank you.
I think someone knows what the Kozai cycle here is.
Yeah, it's kind of dynamically affects. So it's coupling, inclination, eccentricity. You have this kind of modulation that when the eccentricity grows, the inclination goes down, or when the inclination grows, the eccentricity goes down. In coupling with tidal forces, this can lead to a kind of dynamical migration. We don't need any disks. But actually, I wanted to ask you a question. You're welcome. When you present your statistics on this kind of sunspots, occurrence of sunspots, let's say, do you take into account that maybe there is an offset of the number of sunspots with the longitude or latitude of the stars? Sorry. So because I mean, for the sun, we know that it's not equally distributed, right?
Yes.
So when you this actually gives you an indication also about the inclination, or the mutual inclination of the stellar rotation axis to the planetary orbit. If you don't see any sunspots, doesn't actually mean that, or does it actually mean that there is no alignment between those two?
No. Basically, if you've got a transit where you don't actually see any star spot, it just means that the latitude that the planet crossed over at that particular time didn't have any star spots on it. As we know from the sun, star spots, latitudes evolve over time. But we don't constantly monitor transits every consecutive transit, which is why probably the Kepler data is far superior, because you've got continuous transits. And so you can then perhaps eventually see, oh, we've got star spots, we've seen star spots in the light curve for a period of weeks or months, and then suddenly they disappear, which could indicate how an active active band of star spots are moving up and down from latitudes. So just because you don't see any in the transit light curve doesn't mean there is...
Yeah, but I actually meant the converse. So if you see star spots, then you basically know that you have to be at low latitudes, right? Because otherwise, in high latitudes, you don't see a lot of star spots.
No, you don't see a lot of star spots, but it has been known for there to be, say, for example, polar star spots from some more active stars. But generally speaking, you would expect to see them in the mid-range, not too high up.
Okay, well, thank you very much, Jeremy. And as a token of our appreciation for coming here from far, far away, NASA is so far, You have this wonderful cup that you can have
Oh.
your coffee or your tea.
Thank
More tea
you.
than
Oh, yeah,
coffee,
cup
right?
of tea.
Yeah,
Oh,
cup of
yes.
tea.
Tetley's.
Thank you.
Tetley's. Thank you.